How's it going, everyone? Welcome back to today's video. Today we're going to talk about the mole, Avogadro's number, and molar conversions. The mole is something that we use in chemistry for stoichiometry, which is another video we're going to make into the future here, and I'll post a link up here at some point when that video gets made. I'm going to talk a little bit about Avogadro's number, but we're not going to spend too much time on it just because it's got a great history. I'll post a video of another YouTube video you can watch on it, and it's pretty interesting on the significance of it, but we are going to focus strictly on the mole, what it means in chemistry, and molar conversions for when you go and do stoichiometry for a chemistry class or just basic chemistry that you're doing on your own or for a job. Let's go ahead and get started. These numbers, we call it coefficients, just in our balancing chemical equations, these represent the proportions of moles that these molecules here would react with to produce this many moles of this molecule here. And I'm going to take a moment and kind of draw that here. So what that means is when we have two hydrogen atoms, that means it takes two hydrogen atoms and one oxygen molecule, hydrogen molecule, oxygen molecule to produce. And let's make a little difference here. Two molecules of water. And that's what this mole represents, is just since we can't get so small as to just react two hydrogen gas molecules with one oxygen gas molecule, and I don't know if there's any sort of practicality of doing that at all. We have to blow it up into this really large number of molecules that we would refer to as the mole, which equals Avogadro's number, which we'll talk about in the next bit. But what this means is just you cannot react just one hydrogen molecule with an oxygen gas molecule. You need two of these, because when these bonds break, you're going to be left with two oxygen atoms, and each one of these needs two hydrogen atoms. Over here we have two, and there's two over here, so these guys here, these hydrogen gas molecules, can come over here and bond with one of these, but we still need one more, so we would have to have had another molecule or mole of hydrogen gas in order to react with these guys over here, and then we end up with a completely balanced number of atoms of hydrogen and oxygen on each side. So moles is just a metric to represent the total number of molecules that's required, at least proportions of molecules, in order to carry out a reaction to completion. Let's go ahead and talk about Avogadro's number really quick. Okay, let's talk about Avogadro's number. Avogadro's number has a really important significance in chemistry. I don't have the resources and the artistic capabilities to go as far in depth to explain how we figured out Avogadro's number, and it's what we use it for today, but there will be a link down below in the description that I encourage you guys to go watch that video. It was pretty entertaining and educational to watch. But basically, 1 mole is equal to Avogadro's number, and Avogadro's number is just the number of particles that was determined to a certain degree, or to a certain significant figure of particles that are in 1 mole of a substance. So if we had 1 mole of any substance at all, and we'll talk about that here in a moment, of anything on the periodic table or a molecule that was made up of multiple elements, 1 mole of that substance would have 6.022 times 10 to the 23rd particles of that substance in it, whether it's atoms or molecules, whatever it might be. Now, the molar mass, if you guys look in your periodic tables that you might have handy nearby, or just any one of them, that molar mass that was in a previous video, we mentioned it, it's represented in atomic mass units. It's also represented in grams per mole. That is, for every 1 mole of that substance, you have this many grams, and that grams is represented in the molar mass. And in that many grams of that substance, whether it be gold, iron, sodium, whatever you're looking at, it's going to have 6.022 times 10 to the 23rd particles. So one example I wanted to look at was sodium, represented with Na on the periodic table. Sodium has a molar mass of 22.990 grams per mole. That means that if you had 22.99 grams of sodium, you would have 1 mole of that substance. And in this many grams, you would also have 6.022 times 10 to the 23rd atoms of that substance. Let's go ahead and do some molar conversions because that's really why we're all here. Okay, here's how to do molar conversions. We would do molar conversions if we wanted to figure out how many moles of a substance that we had. Say that we wanted to do some stoichiometry, do a chemical reaction, and we wanted to figure out how much of a substance we needed in order to react with another substance. We would do some molar conversions or stoichiometry. There was a video that I made on unit conversions, and we went into depth. All you have to do is watch the simple unit conversions simple unit conversions video, and I will post a link up here, and it goes more into depth how to do that. But here's the basics of what you need to do. The unit conversion factors for how to convert are down here. Basically how to convert between mass and moles and particles. I'm going to explain right here. It's not possible to go from mass to particles. This is why we have such an importance with the number of moles. From particles, we can convert between the number of particles that we know to moles, and then we can convert that to mass, but we can't go straight from mass to particles. That's why I don't show that here. So let's get going on explaining this. To convert between mass to moles, mass in grams of whatever substance that you have. So if you're working in kilograms, you have to figure out how many grams that is. You would multiply that by a unit conversion factor of 1 mole over the molar mass. So for instance, if you were working with potassium, you would multiply the number of grams of potassium that you have by 1 mole over the molar mass of potassium, which is 39.098, and that would get you the total number of moles of that substance that you have. And if you needed to do the reverse, you would just flip that. You would put the molar mass on top over here, multiply that by the moles that you already have, and then you'll get the grams of that substance that you're working with. To go from moles to particles, you follow the same process here. Take the number of moles that you have, and you would multiply that by Avogadro's number, 6.022 times 10 to the 23rd, over 1 mole. And that will get you the total number of particles that you have, given the number of moles of a substance that you have. To go from particles to molecules, it's the same thing as up here. You just flip them. So you take the number of particles that you are aware that you have, and you would multiply that by a unit conversion factor of 1 mole over Avogadro's number, and that will get you the number of moles. So basically you divide it by Avogadro's number over here, while over here you multiply it by Avogadro's number. Let's go ahead and do examples. We're going to do 4 examples total. Okay, first example we'll look at is how to convert from mass to moles. And say you have a reaction and you have 38 grams of iron that's been produced as a result of that reaction. We're trying to figure out how many moles of that iron is. What we need to do is we need to first find the molar mass of iron. It is 55.845. And we are going to multiply these 38 grams of iron times 1 mole on top, because this is our desired units, times the molar mass of iron, which is 55.845. We would multiply across here, and I'm going to go all the way through it just because it helps reduce mistakes when you're doing math. 38 times 1 gets you 38. You would end up dividing that by 55.845. This will be the only time I do this because it is kind of a task. This is grams per mole, and grams cancel out, and that would reduce down to whatever that is, something less than 1. 38 divided by 55.845. That comes out to 0.6 0.68 moles. So this would be how many moles of iron you have in 38 grams of iron. Let's go ahead and do the reverse. Okay, say we're doing a chemical reaction. This is a fun one, putting sodium into water. Please be careful if you guys are doing that. It's pretty reactive stuff. 3 moles of sodium. We want to figure out how many grams of sodium that would be if we wanted to make a small rock of that so that we can throw it for a fun little demonstration. To do that, we want to find the mass of it, so we would put the molar mass of sodium on top for our unit conversion factor, and that is 22.99. And that is how many grams are in 1 mole of a substance. We would go 3 times 22.99, and that would come out to, I'm thinking 60 something. 3 times 22.99, that gets a 68.97. I'm not paying too close attention to significant figures. Please be kind to me in the comments, all you true chemists out there. So this is how many grams of sodium we have if we had 3 moles of that substance, or how many grams we would need if we wanted to have 3 moles of that substance for whatever purposes we have. 68 grams, I think that's kind of a lot of sodium. That's the molar mass right there. Let's go ahead and do some how to convert between moles and particles. Remember, we can't go from mass to particles. We always got to go through moles. So we'll take a look at the number of moles we have, convert it to particles using Avogadro's numbers. Okay, let's say we have 2.5 moles of oxygen gas, and we were trying to figure out how many particles are in that many moles, and it all follows the same process here. We want to convert this to particles, so we're going to put Avogadro's number on top, and that is 6.022 times 10 to the 23rd, and then that's over 1 mole. There are this many particles in 1 mole. In this case, it's going to be molecules. And hopefully you guys have a fancy calculator. Every calculator is a little bit different. We would go 2.5, multiply it by this number because this is our desired unit that we want that's on top. 6.022. That would be times 10 to the 23rd. Hopefully my calculator's got this. And that seems right to me. That is 1.51 roughly times 10 to the 24th power. Pause. Yes, that's right. That's good. Double checked it on my calculator, and that is right. I believe. It would be bad if I posted that on YouTube. Please cut that last bit when you go to edit. That is an absurdly large number. Let's go ahead and go the other way now. Particles to moles. Okay, I just picked a random number here. I have no idea what this is going to turn out to be, but let's say we wanted to take the same number here, 6.022, but times 10 to the 25th power of particles, and see how many moles that is. What we would do is we multiply that by our unit conversion factor of 1 mole over Avogadro's number, 0.022 times 10 to the 23rd, and that equals, let's see here, so that's going to be divided by for that, and this is going to be a wild calculation on the calculator here, so we would go 6.022 E25 divided by 6.022 E23. Enter. That's 100 moles. I think you math heads out there probably could have guessed that, because I guess that's right. Two decimal places over, that would just be like that. That's all I have for today's video, guys. I hope this was informative. I encourage you guys to go watch that video in the description to kind of learn about the significance of Avogadro's number. For the most of all chemistry, we never talk about this Avogadro's number, or at least we never use it. We will mostly use molar conversions, converting between mass and moles, especially when we start talking about stoichiometry and trying to analyze chemical reactions on a quantitative level, and which we'll be talking about in a future video. Thanks again, guys, for watching. Please like and subscribe if this helped, and I hope you guys have a great day.